Hello everyone, my name is Nicole Christoff and today I will present you my article Semantic Segmentation-based automatic wood cell detection from raster images. I work with my colleagues Dr. Nikolai Bardonov from University of Forestry. Well, the outline of the current presentation, I will start with a brief introduction. After that, I will present you the data and some data analysis, the model architecture, obviously this is the solution of the position problem, and a brief conclusion. So, this is a cross-section of a wood tree. As you can see, we can find different type of arrangement of vessels. For example, we can have a solitary vessel, paired, and in group of severals. During the data taken, it is possible to appear, for example, some dust or pores or a wall of the vessel. We can have tearing of the wall actually. So the idea of the proposed algorithm is to find a way to segment all the vessels and to detect them. First of all, let me show you the data. We choose 3 different species, tropical, ring porous, and diffuse porous. For each of the 3 groups, we selected 9 woods, and they are colored in different colors. Why, I will show you now. So let's start with the tropical samples. So for the first line, they are colored in green, and for each of those samples, we can have this type of histogram, and as after deep analysis, we found out that the cells are somewhere here around 140 and 200 pixel values. We can have, for example, for line number 2, we can have our histogram, which is uniform, unimodal, and bimodal for the third part of the proposed samples. With the same type of distribution of pixels, we can have, and we have actually for ring porous and diffuse porous. The idea is to find a way where the 3 huge part of our data are divided, but they have also very similar values. So, as a preprocessing step, we start with some preprocessing step. Actually, there are 2. The first one is resizing, and the second one is normalization. First of all, we have our RGB images, which are resized to 64 by 64 pixels, and after that we normalize the pixels from 0 to 255, which stand for 8-bit images, and this step will ensure the numerical stability during the training and will reduce model sensibility to pixel intensity differences across the images. The dataset annotation, I started with the repetition of the distribution of the pixels, but we will focus also on the shape of the vessel. So here we will use some shapes which we known as geometric primitives, and we can have two of them. The first one is round and the second one can be known as star. So the idea is that during the data annotation we will take those and we will try to draw those shapes over our samples. What is the difference? So for the round shape we will have a diameter and we will try to segment only the cell, the cavity of the cell. The same cavity we will try to segment it with the second type of vessel, star. For this part we will try to segment as many points which are which will describe the form. I will open a small note that there are some samples where the number of the points are impair, which means that we cannot find a diameter. Why it happened? Because of the size and the form of the vessel, and also due to the fact that it's annotated by hand. So it's in the perfect position. We can find a pair number of points, but it can happen to have, for example, to describe better the form, we can take an impair number. During the data annotation, here is the first sample. So from the big images at the beginning that I present you, we will try to segment only one vessel in the middle of our sample, and we will try to take around 5 to 10% of pixel around the vessel. After that we will use software Label Me, which is free to use, open access, and we segment the points which will be represented the form of the cavity of the vessel. And here is the mask, segmented mask. So for the training data set we have 810 samples, and for the validation data set we have 60 samples. All the data set, which mean the samples itself and the mask, can be found in GitHub, and you can download it and use it. Please feel free to use them, and don't forget to link or to cite the current article. Well, this data set was used to train. So we had two data sets. First one was for the training, and the second one is for the test. And we based our algorithm, our model architectures on this architecture. And what we have, we propose three methods or three models, three model architecture. The architecture for the three model is the same, is unit. And what are the different other similarity. As activation function, we usually use a ReLU function, and the first in bottom block we have 124 number. After that, where are the difference? The big, let's say, difference is by the number of convolutional filters per contracting layer, where from the first and the second model they are fixed, and for the third model we have a growing neural network. And another difference is the batch normalization, which we use for the second model. And the third huge difference is the output activation, where for the first and the second model we simulate, and for the third one is ReLU function, and there are small changes of the architecture. For the test, we use the data set for the test, and to find, let's say, the accuracy, precision, recall, and F1 score, we use the well-known formulas, where TP is true positive, we have false positive, false negative, and true negative. After the test, in the same using the same training set and the same test set, our comparative evaluation metrics are the follows. So we obtain a better result for accuracy using the third model, but the precision is better from the first model. Let me show you. So for the first and third model, we didn't use the batch normalization, but if we use the batch normalization, which means the model number 2, we have recall, which is the higher recall of the system. So as a conclusion, we propose 3-unit-based semantic segmentation automatic vessel detection methods for raster images, and those models were trained and tested as annotated dataset that you can find in GitHub. So the most significant distinction between the models are the application of batch normalization, as well as variation in the total number of convolutional layer and their outlier order. Overall, our models provide a promising approach for automatic vessel segmentation in wound cross sections. As future studies, we may improve the models. We can analyze architectural adjustment and determine if they can be extracted to different wood and type of images. We would like to thanks the research and development sector at Technical University of Sofia for the financial support of the publication of the current article, and we also want to thank the Bulgarian Ministry of Education and Science under the national program Young Scientific and Postdoctoral Studies Phase 2. Thank you for your attention. If you have any questions, please feel free to write me an email. Thank you.